Welcome to the course Formal Language and Automata Theory. In this lecture, I'm going to explain about one of the type of pushdown automaton, that is deterministic pushdown automaton. So this is the last topic in unit 3. Here we'll discuss about the definition of deterministic pushdown automaton, followed by the conditions of deterministic pushdown automaton, then some examples also demonstrated here. Now you can see the definition of deterministic pushdown automaton. You can recall the definition of PDA, pushdown automaton. Now during discussion of pushdown automaton, there we mentioned one point. By default, PDA is non-deterministic. By default, PDA consisting of non-determinism. So, but specifically, if your PDA is deterministic, means we have to define separately. Now you can see the definition of a deterministic pushdown automaton. Yeah, the same 7 tuple definitions we have to consider, same as PDA. But if it is deterministic, means some conditions needs to be satisfied. So let M equal to Q sigma tau delta Q naught Z naught F be a pushdown automaton. So here we have taken same pushdown automaton tuple definition. The PDA is deterministic if, here you can see, the following are the conditions of deterministic PDA. The first condition, delta of Q, comma A, comma Z for a state Q with an input symbol A with initial symbol of stack. So this transition has always only one element. That means from a state on same input symbol with initial stack symbol, it has only one element. So you can recall once this condition same as in deterministic finite automaton. So in deterministic finite automaton, you can recall from a state with the same input symbol, it does not contains more than one transition. That means from a state on same input symbol, it has only one next state. That is the condition of deterministic finite automaton. So similar condition is applicable in deterministic pushdown automaton also. From a state with the same input symbol with initial symbol of the stack, it has only one element, nothing but one move. So it has only one move. That is the condition of deterministic pushdown automaton. Then second condition, here you can see, if delta of from a state Q with empty input, that is null epsilon, then initial symbol of the stack. So delta of Q comma epsilon comma Z is not empty. Suppose if this condition is satisfied, then delta of Q comma A comma Z should be empty. Here you can observe the relation between these two conditions. The first condition is with a state Q. Here input is empty. Here input is empty. Here you can see your input is not empty. Here input is there. Now you can see stack also not empty here. Why? Because here it has initial symbol. If null is there, then at the time we say stack also null. Here you can observe, here also stack contains initial symbol. Initial symbol of stack, that is Z or Z naught. So actually, if you can consider this transition with empty input, stack contains initial symbol means compulsory this should be empty actually. But here what we mentioned, this is not empty. But this is always empty. Why? Because no input, stack contains only initial symbol. But we are saying not empty. Suppose if this is not, even with empty input, initial symbol of the stack, we are saying this is not empty. Then here you can see the opposite of this one. From a state Q with an input symbol A, stack initial symbol Z. Here you can see should be empty. Actually, this is not empty. Why? Because here you have input is there. Input is not empty. Stack initial symbol. If input is empty, there may be chance of getting empty. But this is not empty always. So now reverse. So this condition always false. That means here not empty means this condition also always false. Then this condition always true, like that. That means if this is even after seeing empty input, you are saying this is not empty. Then with the input also, this is not empty, but you are saying it as empty. That means if this will possible, then automatically this will also possible. So, but while coming to the reality, this is always empty. Then this is not empty. That means for a state with an input compulsory, there exists at least one element, the first condition. So if you can take this as empty, then this is not empty. But this condition is always empty. Why? Because we have empty input. So this is the second condition. So here, no need to get confusion here. This is very simple. So with empty input with the initial symbol of the stack, this is always empty. If this is always empty means with some input with initial symbol of the stack, this is not empty, consisting of only one element, the above condition. So these are all the conditions of deterministic pushdown automata. So both conditions should be satisfied for the PDA to be deterministic. If one of the condition fails, then the PDA is non-deterministic. So only that is the definition of deterministic pushdown automata. So from a state with one input symbol with empty symbol of the stack, it has only one element. Then from a state with empty input with initial symbol of the stack, this is always empty. Then delta of QAZ is not empty. That means it contains one element. So both conditions needs to be satisfied by any PDA. Then we can say that PDA is called as deterministic pushdown automata. Now let us see one example problem, then you will get clear idea. So the question, sometimes in examination you may get these type of questions. They will give one PDA, they will ask to verify whether is it deterministic or not. Here you can observe the question, is the PDA corresponding to the language L equal to A power n B power n such that n greater than or equal to 1 by final state? Is deterministic? This is the question. So simply here you can follow the same procedure as in PDA design for a given contextual language. After obtaining PDA, by seeing the moves or transitions of PDA, you can check the conditions of the deterministic PDA, the two conditions. So this problem we already discussed in our regular class. L equal to A power and B power n such that n greater than or equal to 1. So directly that solution is included here. So now after the solution, you can observe the moves and you can verify the conditions of deterministic pushdown automata. This problem we already discussed. So number of A's followed with number of B's. This is the nature of the language. First A's, then B's. So in this problem, first we have to push one A onto the stack. Then again you can push the second A onto the stack if stack contains already one A. Then whenever opposite symbol, that is B. Why? Because first number of A's followed by number of B's. So whenever one B is occurred in input, then stack top contains A. So then the stack top element A is erased with the current input B. So here Q1 comma epsilon means erase. Here this is pop A. Always you have to pop element from the stack only, not from the input. Now again, here state is changed. Now you are at Q1. Again, second input is B. Then one more A is on top of the stack. So again, we have to pop the second A. Now you can see. So after erasing all A's from the stack, now the stack contains only initial symbol, that is Z0. Now input is empty. So then it goes to final state here. So here QF belongs to F. So this is the logic of this problem. So now with this PDA, now our condition is you have to check whether is it deterministic or not. This you need to verify by checking the above conditions of DPDA. Now you can see the same problem, a solution is added here. The PDA should satisfy the two conditions shown in the definition to be deterministic. The first condition, delta of QAZ, has only one element. Now in this case, you can see for Q belongs to Q, A belongs to sigma, Z belongs to tau. There exists only one definition. Here you can see for every state Q naught with input A, here you can see with the stack symbol Z, QAZ, here you can see QAZ. It has only one element. That means only one move. Suppose if you will get one more move with the same Q naught, same A, same Z naught. Suppose if you will get one more, then first condition is not satisfied. Always you can see the initial symbol of the stack Z naught or Z, and input symbol A, then a state Q, which has only one element. Only this condition needs to be satisfied. But second transition here you can see 2 naught A, but this is not Z naught. This is not equal to Z naught. Here also this is not equal to Z naught. Here also this is not equal to Z naught. So only with an input symbol, with the stack initial symbol, it has only one element. That is the first condition. So the first condition here it is satisfying. Only in one transition the first condition is included. So remaining other transitions, first conditions not applicable. So now there exists only one definition. So the first condition is satisfied here. Like that for all problems you can verify from a state, from an input with stack symbol. Now you can't take other than initial symbol of the stack. So in this case it has only one element. Now coming to the second condition. To satisfy the second condition, consider the transition. The last one you can see delta of Q1 epsilon Z naught. This one Q1 epsilon Z naught. It is going to final state and here stack is null. Here you can see. Since the transition defined, the transition delta of Q1 A Z naught, where A belongs to sigma, should not be defined, which is true. Here you can see from state Q1 with an input A with the empty symbol of the stack, this transition is not defined. But Q naught A Z naught, that is different. So that's why if this is not there means always this is true. Q1 epsilon Z naught equal to QF null. This is always true because this is empty, always empty. So here this condition delta of Q1 A Z naught, where A belongs to sigma, should not be defined, which is true. So therefore this condition also satisfied because of this one. Now this is true here. Now the first condition, this is true here. Only you can verify these two conditions enough. Remaining no need to verify. So therefore both conditions are satisfied. The given PDA is said to be deterministic. So only you can verify the first condition, then empty condition. So if both are satisfied, then you can say the PDA is deterministic PDA. It is not like deterministic finite automaton. In deterministic finite automaton, from a state with same input symbol, it has only one next state. That is the first condition. Then it does not contains a transition with null, that is epsilon. These two conditions are satisfied in any automaton, then that is said to be deterministic pushdown automaton. Now, whereas in deterministic finite automaton, whereas in deterministic pushdown automaton, from a state with an input symbol with initial symbol of the stack, it has only one element. Then the second condition, from a state with empty input with initial symbol of the stack, then the stack is null. Means this is always empty. This condition is satisfied. Then you can say if any PDA satisfies these two conditions, then that is said to be deterministic pushdown automata. Similarly, you can see one more example. So actually, in design of PDA, we discussed two problems till now. The first one is just now the previous example, L equal to A power n, B power n, such that n greater than or equal to 1. This problem in the previous presentation we discussed. Then another problem we discussed, L equal to W such that W belongs to A plus B whole closure and number of A's in string W equal to number of B's in string W. This problem also we covered. Now the third problem, actually this is the third problem. This is also one of the important problem. Now this is the solution. You can make a note of this solution. So design a PDR, construct a PDR corresponding to the language L of M equal to WCW power R such that W belongs to A plus B whole closure by final state. Now this is the solution of the PDA for this language. Finally, after obtaining the solution, then you can say whether it is deterministic or not. But actually, this language is also called as palindrome strings. Palindrome strings. Sometimes they will ask design a PDA of palindrome strings or palindrome language or L equal to WCW power R. W belongs to A plus B whole closure. Sometimes W they may give with a 0-1 combination also. Whatever the input symbols, no problem. But the language is W, then it's reverse. W per R is the reverse. Whereas C is nothing but it is a character. This you will call it, we will call it as middle of string. Whenever C occurred, it changes the state without changing the stack symbols. So now, if you can see the nature of the language, suppose W equal to AB, then W power R equal to BA. If you can combine these two, WC W power R equal to AB, now C, then BA. So this is the middle of the string. So in palindrome string, the logic is the given string and the reverse of the string should be same. Now the complete string is W power R. So here by excluding this middle of the string, AB, BA. Now you can take the reverse. Again, reverse is AB, then BA. So you will get same. The given string and the reverse of the string should be same. So this is the palindrome language. So now in the palindrome language, here you can see first we are storing the original string W equal to AB, then W power R equal to BA. Now if you can combine these two, W power R by including middle of the string, here you will get A, B, C, B, A. Now this is the first string, this is the second string. In the first string, the last symbol, the second string first symbol should be always equal. So these two we have to pop or erase. Then next time we can see the first symbol, then here the last symbol. These two are equal. So again, we have to pop or erase. That is the logic of palindrome string. That means the input and top of the stack should be same. Then only how to pop. So now here, this is stack. Here, suppose on top we have B. Then if input is B, we can pop top B here. Then second case, stack top is A, then input is A. You have to pop because of this logic. So when you can perform pop after entering into middle of the string, then whenever the top of the stack matching with the input symbol, then we have to pop. That is the logic of this problem. Now we can see with that logic, the PDA is constructed here. Now you can see first what you have to do here, WW4R, the string may start with A, may start with B. Why? Because here order is not given. Simply they have given W. But W is consisting of A-B combination. Whether it may start with A or it may start with B. Suppose all combinations you have to consider. If it start with A, you have to push A onto the stack. If it start with B, you have to push B onto the stack. Actually, this is B. You have to push B onto the stack. Then already first case one A is pushed. Again second A is occurred. Then again you have to push. Then already your stack top contains A if input is B, or because it may start with B, then you have to push B also. Then your stack top is B, your input is A. In this case also you have to push A. Now you can see if stack top is B, input is B. In this case also you have to push. That means here you can see if with the same state only we are inserting all combinations. First A is inserted, then B is inserted, then whenever A is there, one more A. Whenever B is there, one more B. Then on stack A is there, then you can insert B. Then here A is there, you can insert B. Now you can see total 4 combinations: AA, BB, AB, BA. Then initially AB separately. After inserting A, whenever stack top contains A, the other combinations input is A, then input is B. Then whenever stack top is B, input is B, input is A. With the same top symbol, alternate inputs. With the same top symbol, alternate inputs. That is AB whenever A is there, AB whenever B is there. Like all combinations, you have to insert. So now in the same state without changing state. That means before middle of the string. So all these before C, middle of the string. Now once middle of the string is entered, now here you can see Q naught C Z naught. Here simply just change state only. So we can't change the stack symbols here. So the 3 cases here you can see. Whenever C is entered, stack Z naught. Here Z naught remains same, simply changing the state. Then here whenever stack top is A, it remains A. Simply you are changing the state. Whenever stack top is B, B is keeping as it is, simply we are changing the state. Whenever middle of the string is occurred. Now you are at Q1. That means after middle of the string. Now whenever input is A, stack top is A, then you have to pop. Here pop A. Then whenever input is B, stack top is B, you have to pop B. Now, so you erased A and B with matching symbols, matching with same input, with the top of the stack. Then only you can perform pop or erase. Now finally the input is empty, stack contains initial symbol. Then it goes to final state by keeping stack initial symbol as it is. So there here Q2 belongs to F if it is accepted by final state. Here they mentioned final state. Suppose if the PDA by empty stack or null stack, at that time you can keep this as null. Then Q2 not a final state. If Q2 also final state, stack is also empty, then this is accepted with both cases. So this is the logic of this problem. So now this is third solution also, design of PDA. Now, but here our question is this PDA is deterministic? Now you can verify the two conditions. Again, here you can see with Q naught with an input with the initial symbol of the stack. Here you can see we have only one element. Again, the second case also with the different input. Q naught B Z naught. Why? Because wherever Z naught is there on top of the stack with different inputs, we have only one element. Here also only one element is there. But further we don't have Z naught on top of the stack. So the first condition is satisfied. Then coming to the second condition with empty input with initial symbol of the stack. So here the definition is there. This is always empty only. So second condition also satisfied here. So now this PDA is also deterministic pushdown automata. Now here you can see the same explanation is given here. So the PDA should satisfy the two conditions shown in the definition of deterministic PDA. So delta of Q A Z has only one element. In this case, for each state, Q belongs to Q, each input symbol and the stack symbol. There is only one component defined. So the first condition is satisfied. So this is condition 1. Then this is also condition 1. So condition 1 is satisfied, true. Then the second condition here you can see. To satisfy the second condition states that if delta of Q comma epsilon comma Z is not empty, then delta of Q comma A comma Z should be empty. But this is not possible. Therefore, this is also not possible. Then reality, this is always empty. Then this is not empty. So if there is an epsilon transition in this case, here you can say delta of Q1 epsilon Z naught. Here you can see Q1 epsilon Z naught. Then there should not be any transition from state Q1 when top of the stack is Z naught, which is true. So from Q1 state with the top of the stack is Z naught, we don't have any transition. So that's why this is always true, this condition. Therefore, both conditions are satisfied. Therefore, the given PDA is deterministic PDA here also. Like that you can verify. Some cases, if any one condition fails, then even one condition also fails, then that is not deterministic PDA. Then what is that? Non-deterministic PDA. Suppose here, if we have one more transition, let us say some Q1 comma null. Now here you can see from a state with an input with stack symbol, here you have two elements. So now here it is false. Then this is not a deterministic pushdown automata. Even one condition fails, then no need to verify second condition. Automatically, it is not a deterministic pushdown automata. Then what is this one called as? By default, it is non-deterministic pushdown automata if it won't satisfy the conditions of deterministic pushdown automata. Now, that's all about checking off a PDA is deterministic or not. Now, whenever we are talking about a deterministic pushdown automaton, then its corresponding language, which is called as a deterministic context-free language, DCFL. So how can I define DCFL? A context-free language is said to be deterministic if it is accepted by DPDA. So DCFL is accepted by deterministic pushdown automata. Means any CFL is accepted by DPDA, then the CFL is deterministic context-free language. That is the condition. Suppose a context-free language which is not accepted by a deterministic pushdown automata. The above two examples what we demonstrated, those are all examples of deterministic pushdown automaton. You can take any context-free language which is not accepted by any of the above DPDS, then that context-free language is not deterministic context-free language. That is the only condition you need to verify. Now here we have one relationship diagram of different types of languages. First, regular language, context-free language, and deterministic context-free language. So the relationship is shown in the following diagram. Here you can see first the least space language. Here we have represented regular language. Then higher than regular language, we have defined deterministic context-free language. Then the top one is context-free language. This is the relationship represented diagrammatically. Some examples also given here. Regular language, you can see L equal to AB whole power n such that A comma B whole closure. So which is a regular language. Then deterministic context-free language. Here you can see A power n, B power n such that n greater than 0. So this is a deterministic context-free language. For this, we already demonstrated DPDA. Now you can take any string from this language, then you can verify the acceptance with this PDA. It accepts. Therefore, this language is called as deterministic context-free language. Whereas other language, context-free language, normal context-free language, WCW power R. For this, we obtained DPDA. Now you can take any string from this. So if it is accepted by this DPDA, then this is also DCFL. If it is not accepted, then that is normal context-free language, but it is not a deterministic context-free language. So this is one example. Now this is the relationship diagram of regular languages, context-free languages, and deterministic context-free languages. So then the last concept in deterministic pushdown automata. So we have one prefix property of a context-free language. So how to define a prefix property? So during the fundamental concepts of automata theory, we discussed various string operations. So in string operations, one of the concept is prefix, suffix, proper prefix, proper suffix. So then for CFL, we will define the prefix property also. How to define this one? First of all, a language L has a prefix property. The condition is if there are no two different strings X and Y in L such that X is prefix of Y. Suppose you can take two different strings in language L. So the first one is prefix of Y. So this doesn't exist here. This doesn't exist. So here no two different strings X and Y in L such that X is prefix of Y. This case not occurred here. Then we can say the contextual language has prefix property. For example, let us take the previous example language L equal to WCW power R, where W belongs to A plus B whole closure. Has a prefix property. That means in L, there are no such two strings with one is prefix of other unless they are the same string. So when this will possible means whenever both strings are same. So let us see here W equal to 0, 0, 1. Let us say X. Then W power R equal to reverse. So W power R 1, 0, 0. So 1, 0, 0. Let us say Y. Now you can combine these two 0, 0, 1. See 1, 0, 0. Here you can see this is X, this is Y. Here you can see X not equal to Y. X is 0, 0, 1. Y is 1, 0, 0. So these two are not equal. So unless if these two are equal, for example 0, 0, 1, again 0, 0, 1. Now here X, Y equal. Only in this case, this condition is satisfied. But here X not equal to Y. So therefore no two strings are exist with one is prefix of other. Only in case of both are same, then only this condition is satisfied. Therefore, this has a prefix property. Like that, you can check the prefix property of a context-free language. Okay, now let us come to the summary of this lecture. What we discussed related to deterministic pushdown automata. So here first we discussed about definition of deterministic pushdown automaton. Then checking a PDA is deterministic or not. Is deterministic or not with examples are demonstrated. Then what is deterministic context-free language? So if any context-free language that is accepted by a deterministic pushdown automata, then that is said to be deterministic context-free language. Then prefix property of CFL followed by the relation of regular language, context-free language and deterministic context-free language also demonstrated.